Today's lesson is all about putting everything together. So up to this point, we've worked on finding local extrema, intervals of increase, decrease, points of inflection, intervals for concavity. So we're going to put all of that together in order to complete a full sketch of the functions that you're given. Okay? So in order to do that, we're going to follow the algorithm for curve sketching. The first thing we want to do is to determine the domain of the function. Okay, make sure that if you have, obviously if you have a polynomial function, it's going to be continuous on xer, so that's not an issue. But if you have a rational function, for example, make sure that your denominator does not equal 0 because we don't want any undefined values. And if you have a function with any rational exponents or roots, make sure that your radicand is greater than or equal to 0 when you have an even number for the root. So what I mean by that is if you have f of x equals x to the 1/3, in this case, because this 3 is an odd value, that means that our domain is going to be, x can be any real number. Okay, so you can take the cube root of a positive or negative number and get a real answer back. That's not an issue. However, if you have a function like x to the 1/4, in this case, because this 4 is an even number, we need to make sure that our domain is restricted to only positive values of x and 0, okay? Because we can't take the 4th root of a negative number. The next thing we're going to do is to figure out the y-intercept and, if it is easy to do so, any x-intercepts for the function. So in order to figure out our y-intercept, we would set x equal to 0. And if we want to find our x-intercepts, we want to make sure that our y is equal to 0. And for this specific case, this means that the numerator of the rational functions should equal 0 if you want to figure out the x-intercepts. Okay? If the polynomial is not factorable whatsoever, just pay attention to the degree because it indicates the maximum number of x-intercepts that are possible. And lastly, take note of the leading coefficient. This will indicate the end behavior of the function, along with the degree of the polynomial. So, for example, if you have a leading coefficient of -5 and it's a degree 2 polynomial, then we know that the end behavior is going to be from quadrant 3 down to quadrant 4. Okay. Also, we need to take note of any symmetry. If you remember from advanced functions as well, if you have f of -x equals f of x, this meant that the function was an even function, which meant that there was symmetry along the y-axis. So meaning if you take the original function and you reflect in the y-axis, that would give you the same as the original function back. Okay, if f of -x is equal to negative f of x, then that meant we had an odd function. And for odd functions, we had rotational symmetry, meaning that we could rotate the function 180 degrees along 0, 0, about the origin, and we would get the same function back. which really means that if you reflect the function on the x-axis, it would be the same as giving you the reflection on the y-axis. Now, the next part is all about asymptotes. For your asymptotes for rational functions, obviously, this does not apply to polynomials. To get your horizontal asymptotes, the shortcut that we learned in advanced functions was we compared the degree of the numerator to the degree of the denominator. And really, to figure out the horizontal asymptote means that we want to determine the limit as x approaches positive or negative infinity. Horizontal asymptote, that's the limit that we're evaluating, but it's obviously faster to take the shortcut. Okay, if the degree of the denominator is less than the degree of the numerator, the horizontal asymptote is y equals 0. If the degree of the numerator and denominator is the same, then the horizontal asymptote is the division or the quotient of the two leading terms. Okay? And then if the degree of the numerator is higher than the degree of the denominator, then there's no such thing as a horizontal asymptote, because instead you will end up getting an oblique asymptote instead. For oblique asymptotes, while we're talking about it, you can compute long division. When you compute long division, your oblique asymptote is always going to be the remainder. And last but not least, for your vertical asymptotes, you're looking for the values of a, where a is a 0 of the denominator, but not of the numerator. Because keep in mind, if it is a 0 of the numerator as well, then really you don't have a vertical asymptote, you just have a removable discontinuity. Before we move on to the last page, I'm sorry, I made a small error here, so I'm just gonna correct that. This shouldn't be remainder, it should actually be quotient. My apologies. Okay, let's move on to the next page. The next thing we want to do is figure out the local maxes and mins. So that's the extrema. We want to figure out the concavity as well as any points of inflection that we may have. So remember, the first derivative test, this one always works. The first thing you would do is figure out your derivative, first derivative. Okay. Then afterwards, you want to find any critical points where the first derivative is equal to 0 or it does not exist. Okay, then what you want to do is create a sign chart or an interval table for the first derivative, and then you should find the intervals of increase or decrease. Okay, so increase if the first derivative is positive, decrease if the first derivative is negative. And keep in mind, if the first derivative at x equals c changes sign from positive to negative, that means you have a local maximum. And if it changes sign from negative to positive, it means that you have a local minimum. So at this point, we're going to change from positive to negative for our first derivatives, and then that's why we have a local max right there. Or we will change from negative to positive, and therefore have a local minimum right there. And if the function is defined on a closed interval, then you can find your global extrema using the extreme value theorem. And just to remind you how extreme value theorem works, you take your critical points and your endpoints, you sub them in for the x value into the original function, and you figure out which one is your highest and your lowest values, and that will give you your absolute max and absolute min. And then again, if you want to use the second derivative test instead to find your local extrema, it is faster, but only if it works. So if your first derivative is equal to 0 at some x value of c, and if your second derivative is positive for that x value of c, then you're going to have a local minimum. Okay, if you have, sorry, I need to fix this. If your first derivative is equal to 0 and your second derivative is negative, then you're going to have a local maximum. Second derivative negative, again, at x equals c, then you should have a local maximum. So going back to these examples here, you have this function. So at the point x equals c, you have a local maximum, and it's because the function is concave down, so that's why your second derivative is negative. But your f prime is equal to 0. So that's, you put these two together, and that's why you get local maximum here. And then for the other example, at x equals c, your f prime of c is equal to 0, but your function, your second derivative, is positive, and that means that your function is concave up. So put these two pieces together, and that's why you have a local minimum. Okay. Remember, second derivative test fails if your second derivative is equal to 0, because in that case, you could have local extrema, or you might have a point of inflection. Now let's move on to concavity and points of inflection. So to figure out this information, you want to compute your second derivative and then figure out your points where the second derivative is equal to 0 or it does not exist. Okay. Then you have to create the sign chart or your interval table for the second derivative. And your points of inflection exist where the second derivative is equal to 0 and the second derivative changes signs. I will add in also that it could be where the second derivative does not exist, such as at an infinite slope point. Okay, the second derivative won't exist at an infinite slope point, but the second derivative does change signs to the left and to the right of that point. So that's why it's the point of inflection. Okay, and then just keep in mind that the function is concave up when the second derivative is positive, concave down if the second derivative is negative. Once you've done all of this, the last thing you want to do is sketch your function using all of the information that you've gathered. Okay? Figure out where your intercepts, extrema, and inflection points are and plot those points first. Okay? Any asymptotes that you might have for rational functions, make sure you draw them in using broken lines. And then you can draw your curves near your asymptotes to complete your sketch. So let's move on to some examples on the next page. So looking at this function, we can see that it's going to be continuous on its domain because it is a polynomial function. So that's the first thing we notice. And then the next thing we should do is to figure out any intercepts. Okay, just looking at the last term here, we don't have a constant term, so we know that automatically the y-intercept is going to be 0. And if the y-intercept, so let's start by plotting some of these points. Okay, our first derivative, and that will give us our intervals of increase, decrease, and then any local extrema. So f prime is equal to 3x squared plus 12x plus 9. If we set f prime equal to 0, there's not going to be any values where f prime does not exist. It's a continuous polynomial function. So we can just focus on f prime equaling 0. And that will help us figure out our critical points. And again, lucky, we have a factorable trinomial. So at x equals -3 and x equals -1, these are our critical points. Now, because this is a polynomial function, I'm not going to use the first derivative test. Instead, I will move on to figuring out the second derivative. And I'll use the second derivative test instead to determine whether or not I have local extrema at these 2 points. So my second derivative is going to equal 6x plus 12. Again, there are no points where the second derivative does not exist because this is a polynomial function. So I can just set it equal to 0 and solve for x equals -2. So this is going to be possibly a point of inflection. So to figure that out, let me create a number line or an interval table. Okay. So I'm going to put -2 here. This is towards -infinity. This is towards positive infinity. So when x is less than -2, then 6x plus 12 will be negative. When x is greater than -2, 6x plus 12 will be positive. So this means that the original function f of x is going to be concave down when x is less than -2 and concave up when x is greater than -2. And then because I have my 2 critical points at -3 and -1, -3 will fall here when x is less than -2. So I know that the second derivative is going to be negative. So second derivative of -3 is going to be negative. And when the second derivative is negative and f prime, the first derivative, is equal to 0, then we know that we're going to have a local maximum. And we'll repeat this for second derivative of -1. That's over here in this interval where we know that the function is going to be concave up, so the second derivative is positive. So that means we are going to have a local minimum at x equals -1. And to figure out the actual y-coordinates of those points, you're going to have to plug them into the original function. So f of -3 would equal -3 cubed plus 6 times -3 squared plus 9 times -3. So when you do the work, it should equal, let me see here, it should equal 0 because we already figured that out here, -3, 0. Okay? And then if you have f of -1, -1 cubed plus 6 times -1 squared plus 9 times -1. Figure out the y-coordinate, calculate, and you should get a y value of -4. So we can put this -1, -4 on our graph here. That's going to be a local minimum. Okay? And we know that because f prime prime at -2 is 0, and the sign changes from negative to positive, that means we do have a point of inflection at x equals -2. So we need to just calculate what that's going to be. So when you put in -2 for x, just calculate what the y value should be. And you should get -2 back is the answer. -2, oh, sorry, I just made a mistake there. -2 is our point of inflection. So now you can join all of the points that you have together into a smooth curve for your sketch. Just keep in mind, because we did say that this was a double root, that means that the function does not start up here, it actually starts in quadrant 3, which we should also be able to see because we have a polynomial of degree 3 and the leading coefficient is positive. So the end behavior should go from quadrant 3 to quadrant 1. Okay? So your sketch is going to look something along the lines of like so. If you would like to make your sketch a little bit more accurate, you can add in another point here or another point here, but it's not necessary if you've shown all of this work. So let's move up the page and work on example 4. We're going to get an interesting graph for example 4 because we have x times 5 minus x raised to the exponent of 2 over 3. First of all, we know that this is a continuous function because we can take any value of x here, no restrictions, as well as here, because you can always take the cube root of any number, get an answer back, whether it's positive or negative, and then raise that number to the exponent of 2 to get a positive answer back in the end. Okay, so there are no restrictions whatsoever. So our domain is going to be x belongs to the set of real numbers. So that's the first thing. So now let's look at our intercepts. Okay. So to set our y equal to 0, that should help us figure out what our x-intercepts are. And I can see right away that we'll have 2 x-intercepts at 0 and at 5. So let's start plotting those points down. And because we already figured out that one of the x-intercepts is 0, 0, that's also going to be the y-intercept. You can't have more than one. So mysterious squares, but I made some mistakes earlier, so I'm just going to start over with my first derivative. So here I go. First derivative calculation, derivative of x is 1, leave 5 minus x to the 2/3 alone, and we have to add x times the derivative of 5 minus x to the 2/3. So this is product rule that I just applied. So now this is going to be 5 minus x to the 2/3 minus 2x over 3 times, actually instead of cube root, let me just write it in rational form for now. So 3 times 5 minus x to the 1/3 in the denominator. Then I need the common denominator of 3 times 5 minus x to the 1/3. So that is going to give me a numerator here of 3 times 5 minus x. Because when I multiply 5 minus x to the 1/3 with 5 minus x to the 2/3, 2/3 and 1/3 add together, the exponent overall will be 1. Then when I multiply and add together, I get 15 minus 5x over 3 times cube root of 5 minus x. This is my first derivative, and now I need to figure out where it's going to equal 0 and where it will not exist. So it will equal 0 when the numerator equals 0. So that gives me 5x is equal to 15, x is equal to 3. So here's one critical point. My other critical point will be when the denominator is equal to 0. So f prime does not exist when 3 times cube root of 5 minus x is equal to 0. So divide by 3, you still get 0, and then cube, you still get 0. So really, we're looking for 5 minus x equals 0. So this will be when x is equal to 5. Okay. I'm just going to create a number line at this point just to see what my intervals of increase and decrease look like. So here's 3, here's 5. If I choose a number like 2 and I plug it in here, then positive, positive, so overall positive. A number like 4, positive, negative, and then positive, so that'll be negative overall. A number like 6 and onwards, that's going to be negative, negative. So overall, positive. So this should tell us that we actually have a local from positive to negative. So this is going to be a local maximum at x equals 3 and a local minimum at x equals 5. So the minimum will be 5, 0. And then this maximum, local maximum, I'm going to have to calculate when x is equal to 3 what the original value of the function will be. And when I plug in 3 back in, I should get approximately 4.76. Okay, so now let's figure out the second derivative, and that will help us figure out our intervals of concavity, as well as any not critical points, any points of inflection. So use your quotient rule to figure out what your second derivative should be. One thing I will do is I will say that this is equal to 5 over 3 times 3 minus x over cube root of 5 minus x. And that way I can just leave the 5 over 3 outside when I take the second derivative. Okay. So derivative of the numerator is negative 1, and then cube root of 5 minus x minus 3 minus x, and this is going to be 1/3 5 minus x to the negative 2/3 times negative 1 all over cube root squared. So a little bit messy, but we're going to have to simplify it. So negative, negative will turn into positive. And then here we have 3 minus x times 1/3. 5 minus x to the negative 2/3. And then this is going to be 5 minus x to the positive 2/3. The common factor here is 5 minus x to the negative 2/3. So let's factor that out. And then inside the brackets here, we're going to be left with a negative 5 minus x, because 1/3 minus negative 2/3 is positive 1. And then plus 1/3 3 minus x. over 5 minus x to the 2/3. And then when you combine these two into the denominator, the new exponent is going to be 4 over 3. And then this, when you expand it out, this is going to be 1, negative 1/3 x minus 5 plus x. So you're going to get, let's see, negative. Actually, an easier way to do this would be to, at this step as well, just factor out the 1/3 here. And then instead, you can have a 3 in front of this 5 minus x. And then that way we can combine these, and then we will have 5 times negative 15 plus 3, negative 12, and then 3x minus x over 9 times 5 minus x to the 4/3. And then last but not least, you can factor out a negative 2 here, so this will be negative 10 times 6 minus x over 9 times 5 minus x to the 4/3. So we again need to figure out where the first derivative does not exist or where it equals 0. So we know that, or sorry, the second derivative, it equals 0 when 6 minus x is equal to 0. So that means that x must be equal to 6. And then the other value that where the derivative does not exist will be where the denominator is equal to 0. So that's really when x is equal to 5. So the last thing we need to do is our number line for the second derivative. So 5, 6. Okay, plug in the values, test values of, let's say, 4, 5.5, and then 7, and figure out where your second derivative is positive and negative. So it turns out that when x is less than 5, you should get negative. And then when x is between 5 and 6, you should still get negative. Okay, because this answer will always be positive. So really, we're just relying on this numerator. Okay. And then when x is greater than 6, you will have positive. So that means that the function will be concave down, and then concave up. So you can see that at x equals 5, we do not have a point of inflection. Okay, first of all, we figured out that it's actually a local minimum. And it can't be a point of inflection because the second derivative doesn't change signs. Okay, but here, where the second derivative changes signs from negative to positive, so at x equals 6, we will have a point of inflection. So at the point f of 6, which is going to equal 6, that's a point of inflection. So now we can plot all of this information and graph. So 3, 4.276 is approximately here. And we said this is going to be 5, 0, which is a local maximum, local minimum, as well as being an x-intercept. Okay, so now we can put everything together. The function is increasing until you get to 3, then it decreases, and then it increases back. Okay, and the point of inflection was at 6, 6. Okay. And then we have still concave down from 5 to 6, and then from 6 onwards, it changes ever so slightly to concave up. And keep in mind that this is an example of a cusp point being a local minimum. Okay, the last page is just a quick recap of the sketching algorithm. So let's move on to that. So remember, a function is increasing when the derivative, first derivative, is greater than 0. And a function is decreasing when the first derivative is negative. Now the next part, critical numbers. C is called a critical number if C is in the domain of the function and if f prime of C is equal to 0 or f prime of C does not exist. If f prime of C is equal to 0, then we might have a local max or min. We could also have a point of inflection. So let me just give you a quick sketch of some examples. So here, if we have a function that looks like so, then we will have f prime of C equaling 0, and then we have a local extrema, the local minimum. Or we could have a local maximum. But we could also have a point of inflection like so. So just because the first derivative is equal to 0 does not necessarily mean you automatically have local extrema. It means that you need to do the first derivative or the second derivative test to check. Same thing goes for f prime of C not existing. We could again have local extrema, or we could have a point of inflection. And this would be for corner or cusp points, the local extrema. The point of inflection would be for infinite slope. So we have, let's see here, corner point, there's your local minimum. F prime of C does not exist. We could have a cusp point, like so. Again, our f prime of C does not exist. Or we could have a point of inflection for an infinite slope point, in which case, again, your f prime of C does not exist. But this is not a local max or min, it's a POI. Okay, keep in mind, if the first derivative changes signs from positive to negative at x equals c, then that means you're going to have a local maximum. And if it changes from negative to positive at x equals c, then you will have a local minimum. Okay, so always easiest for sketches just to give a parabola as a very simple example. Okay, so at x equals c, our first derivative will equal 0. To the left, our first derivative will be negative, and then to the right, our first derivative will be positive. Okay, so change of signs, we have a local min. From negative to positive, local min. And then we have here, like so. Again, f prime of c is equal to 0. To the left, we are going to have f prime being positive. To the right of c, we will have f prime being negative. So that means we have a local maximum. And keep in mind, just because the first derivative changes signs, or sorry, just because the first derivative is equal to 0, does not mean that you have a local max or min. So again, this example where f prime of c equals 0, but the first derivative never changes signs. So in this entire interval, f prime is always positive. It doesn't change sign, so that means that f prime of c, or sorry, f of c is not a local max or min. All right. Points of inflection and concavity. So the test for concavity, if the second derivative is positive, then the graph is always going to be concave up on that interval. If the second derivative is negative, that means that the graph will be concave down on that interval. All right, now for the possible points of inflection, you want to look for where the second derivative is equal to 0, so you solve that equation, or you determine where the second derivative does not exist. And usually this happens where the denominator of the second derivative equals 0. Use an interval chart to determine on which intervals the second derivative is positive or negative. And then a point of inflection will only occur when the sign of the second derivative changes. Okay. Last but not least, the second derivative test. If the first derivative at x equals c is equal to 0 and the second derivative is positive, then that means that you have a local minimum at x equals c, because this means that the function is concave up. Okay, so concave up and a critical point, we're going to have a local minimum. Okay, if the function is concave down on that interval and the derivative of the x value is equal to 0, then we're going to have a local maximum at x equals c. I'm going to move up the page and we're going to just go over a few quick diagrams to illustrate. So how about this example? Let's call this C, let's call this, let's call this point right here D, and let's call this point E. Okay. So we are going to have f prime C equaling 0 and f prime E equaling 0. And then, because our tangent line slopes are all positive but gradually decreasing, so that means that our f prime prime is going to be negative, which explains why the function is concave down. And that's why we have a local maximum at f of c. On the other hand here, on this part of the curve, our tangent line slopes start off negative, but they are gradually getting closer and closer to zero until they get to zero at the minimum, and then they will increase. They will become more and more positive. So if your f prime is increasing, then that means that the second derivative has to be positive. So therefore, the function is concave up. Okay? And overall, that means that we have a local minimum at x equals e. And just keep in mind for f of d, the first derivative is going to equal 0, but the first derivative was negative all throughout. Okay, all of the tangent slopes are negative. So there's no sign change, so it's not a local max or min. And because the second derivative is also 0, but the second derivative does change signs from negative to positive, then we have a point of inflection. And that's it for the summary on graphing.